Hello everybody! Thank you for joining me today. This is episode number 2 of Rates of Reaction. Today we are actually going to look at rates of reaction, the different factors and the experiments linked with that as well. Okay, let's get started. The rate of reaction, also our title for the unit 1 in that 5. It's a very crucial topic. First, the factor that contributes to the rate of reaction is number 1, increasing the concentration of a solution. Some books may say that it could be the particle size, like reducing the reaction vessel or things like that, but you could just say increasing the concentration, as it means there are like more number of particles in, like, I don't know, the same 1 cubic centimeter cubed or something like that. Like in one space, the equal amount of space, there are more particles. That means there's more concentration and likely there'll be more collisions because it is more compact. Okay. There is also the one of decreasing the particle size of a solid. Oh my god, what happened to my highlighter? So decreasing the particle size of a solid, which just means if you have this one big lump and you're trying to make a chemical reaction for it, it probably will react very slowly because there's not a huge amount of surface area, whereas if you divide it into little chunks, it'll dissolve or react more quickly. Next will be the temperature. As the temperature increases, so does the rate of reaction in general. And fourthly, there is adding a catalyst, which I will touch on later on as well. So these are the 4 main types of reaction: concentration, particle size, temperature, and catalyst. There's only 4, so I urge you to remember all of them because it's quite useful to do so as well. Let's look at concentration first. Concentration. Now, we are going to look at the experiment related to concentration now, and if you've done some of the scientific experiments, you would be expected to know the aim, the method, the hypothesis, the evaluation, the conclusion, the results, and so on and so forth. In this quick video, we're just going to look at the method and the results. So let's look at the method for an experiment related to concentration. So we have a test tube rack, HCl. The other is also HCl. The only difference is that this is 4 moles and this is 1 mole, okay? This is a marble lump. And this is also a marble lump of the same size, so we're getting everything the same, just the concentration. How could I express that this is of a high concentration? Probably using some black will probably help. This is like a higher concentration, kind of has more particles, and you get the idea. Now, you kind of have noticed that I have added this kind of effect here. It kind of hints how the rate of reaction will occur. So this is the result. The concentration. If there's high concentration, then the reaction speed is fast. If there's low concentration, then the reaction speed is slow. You could think about this diagram. So these boxes have the same shape. One has a low concentration and one has a high concentration. Increasing the concentration of a solution increases the number of particles in a solution, or increase the number of particles per unit something squared. So more particles means there can be more collisions, linked back to the collision theory that we discussed earlier, and therefore the rate of reaction increases. Increasing the concentration of a solution increases the number of particles in the solution. This is one of the key points that I want you to take from concentration today. Okay, let's move on to particle size now. Similar, looking at the method. So this time we have the same. I'm just going to do it like that. 1 mole of HCl. If you don't know, HCl stands for hydrochloric acid, just in case you don't know. And this test tube rack, this has a marble lump. Whereas this one has a marble powder. I have included some hints in the diagram, but which boiling tube do you think will show the fastest reaction? Pause the video and continue when you have the answer. Now we're going to look at the results. As you see, as the particle size decreases, so the surface area, particle size or surface area, as the particle size decreases and surface area increases, and the reaction speed is faster. And on the contrary, if the particle size is bigger and the surface area is smaller, then the reaction would be slow. You could think of it as this. I have actually a very nice diagram. I just have no idea what color I should pick. Ooh, I love this color today. So, say we have a large particle. You want the reaction to occur as quickly as possible. Now I'm going to give you some options. It's option number 1, and this is option number 2. Which decided size do you think will react more quickly? The answer will probably be number 2, as we've seen in this results table example. As the particle size decreases and the surface area increases, the reaction goes and performs much faster, and we want it to perform faster normally. Another key point for particle size: as the particle size decreases, there is a larger surface area. This means there's more surface for the particles to collide with, therefore rate of reaction increases. Always remember the sweet little popcorn diagram that will haunt you through the rest of your life. Now we come to look at temperature. And first, should we look at the method of the experiment that we are going to conduct? Okay, there are 2 beakers this time. Let me just write beakers just in case. And there are 2 boiling tubes as well. The only difference in this experiment will be the water and the temperature of the water. So it is hot. There's hot water in one beaker surrounding one boiling tube like that, and in the other there's eventually no liquid surrounding it, or if there will be, it will probably have to be less hotter than this one, so there is kind of like a comparison between those two. Now let's look at the results of the experiment. As the concentration increases, the reaction speed increases. No, this wasn't supposed to be concentration. This was supposed to be temperature. As the temperature increases, so it could be hot, in other words, high is also good as well, or cold, if there is... what happened here? You know what? It's gonna be a bit smarter. Yeah, that's much easier to... As the temperature increases, it gets hotter, then the reaction speed increases, and vice versa for temperature as well. If there's low temperature, therefore it's cold, then the reaction speed decreases. Why? You could kind of think that these are two separate spaces. Okay, this one is cold, and this one's hot. Probably all of you guys would have experienced coldness. When you are cold, you don't want to move much. You could think that that would be the same in particles as well. So it wants to stay. It doesn't want to move. They're like staying. They're frozen. Yeah, like frozen because Elsa has cast some spell on them. So they're cold. Therefore, they don't move much. Whereas if they're hot, you probably have experienced hot when you're hot as well. You're sweating, your heart beats faster, so your body is moving kind of faster. Your organs are being more active. You're sweating. You're like exhausted, and you could think that in particles as well. They're exhausted. They're like moving really, really fast. They're like speeding. So as you can see, as the temperature gets hot, there's more movement, there's more like vigorous, violent movements, so the reaction speed goes up. If they're cold, the particles don't move. Okay, when the temperature of a substance is increased... Oh my god. This increases the kinetic energy that the particles have. Lastly, we are going to look at adding a catalyst. Adding a catalyst lowers the amount of energy particles need to start reacting. It could also be known as activation energy. Okay, if you kind of don't know what this means, it just means that there's like this amount of energy that you need to trigger a chemical reaction, but the catalyst kind of decreases down into like not like that teeny beeny amount, like that. So the reaction happens much quicker because only this amount of energy is needed, which is a good thing, kind of. Okay, so I'm going to have to draw that good old diagram again. The good old diagram. The one that's peculiar with this one is that it has, I'm just going to match the color. It has a catalyst as well this time. In this instance, it's copper. Oh, I'm so sorry. This wasn't supposed to be a marble lump. This was supposed to be zinc. So it has a copper catalyst. Quite cool. Let's look at the results now then. Okay, this catalyst copper's kind of like... Oh my god. Oh my god. What happened? Results. With or without catalyst. With, fast. Without, slow. Because it lowers the amount of energy needed the particles need to start reacting. Okay, so the reaction happens much faster.